I'd like to welcome everyone to the next lecture of Voyages in Language Technology. And we acknowledge First Nations people as the original inhabitants and the traditional owners of the land on which this course was developed and is being delivered. This land is Meanjin, also known as Brisbane. We pay deep respects to all elders past, present and emerging on this land and the lands from which we are presenting and attending. Today, we have Dr. Ash Rahimi, who is a lecturer in the School of ITEE at UQ. And it's a great pleasure to welcome Ash to talk about some of his favorite work, getting to really understand some of the deep models, the ways in which we think about language from a computer science point of view. And Ash, I'll leave you to introduce your topic and tell us more about it.
Sure. Thank you, Janet, for the introduction. I'm very happy to be here to talk about languages in general and language technologies in particular. I am interested in both, like the study of how languages work and their preservation, and also how to teach machines to work with languages, to understand them, and also sometimes to generate them. They're not very smart, but they can babble. Okay, so today we're going to see language technologies that can help you both understand language a little bit, not really understand, just help you to build applications, and also to generate language. Again, not really, to generate a sequence of words that is interesting, right? So let me share my slides. Okay, so the topic is language models and language generation. What is a language model? That's what we will talk about. So the things we talk about is what is a language model and how we train them, because we need, the language model is like a baby, a very, not really, not babies are much better at learning languages, but it's like a robot baby, right? that learns the language. And then we will see how to learn it from text, large amounts of text, how to evaluate it to see if it can actually learn anything. And then we will see their shortcomings, right? And some of really recent language models in action. So to tell you about the importance of language model in language technologies, it's enough to say they have transformed the field of natural language processing. Few years back, like 4 years back, they were just a small part of natural language processing. If this was natural language processing, this was language models, right? But today, if this is natural language processing field, like the number of papers in this field, half of it, maybe 2/3, is about language models. So they have really transformed the technologies that are used to understand and apply machines to work on text data and also speech data. Okay, so for a starter, we all have search Google, right? When you do a search, a query, Google is able to finish your query, right? Give you suggestions. How does Google do that? Anyone have an idea that wants to share? I know you're all sleepy and I appreciate you getting up in the morning, but is anyone want to write a sentence or two on chat to have a guess, or maybe you know how Google finishes these sentences? Yes, so that's correct, Lucinda. So it states about what people have asked before. So it knows what people have asked before and uses that to make a prediction. Ariane, maybe originally using some sort of learning trees. So they might be using trees in the back end, we don't know. So yeah, that might be an interesting idea. But whatever technology they're using a language model, right? What is a language model? It is a model that can predict next words from the context, right? So here in the query box, you have a context or history of words, right? What you want to do is to predict the next word, right? You have a large amount of queries that people have submitted to Google. And what you want to know is that what is the most probable word after how to make. Depending on the text history that you have, this might differ, right? If it is close to Christmas, it might be something else. If it is like March 2020, it might be face mask. Today, it might be something else, right? Okay, so language models are technologies that help us do this task. What is the most probable word after how to make? How to make is our history, and we want to predict the future words, right? So these models see text as a sequence of words or sequence of characters. So they don't really understand language. They just see a sequence of objects, similar to sequence of like proteins in DNA. So they have no idea what they are. They just predict the next ones based on history. Okay, so formally, language models have been in the field for maybe 50 years, right? So when they started building machine translation model, at the beginning, they had the language models, so they're very old. Formally, a language model assigns a probability to a sequence of M words, right? So here you have two sequence of words, and it has no idea of the sentences or anything. It is just a sequence of words, and it assigns a probability to each one based on how many times it has seen it in their text corpus. So for example, probability of how to make face masks, face mask might be something. This is just the number I've put here. But the intention was to show that the probability of how to make I was, which is not a grammatical sentence, right? So you don't expect to see this anywhere, right? So the probability of how to make I was should be way lower than how to make face mask in Google's history of queries, right? So a language model assigns a probability to a sequence of words, and we expect that the sequences that are more probable, more useful, are not more useful, I mean more frequent, are assigned a higher probability, right? Any questions about this? On what language models are? Okay. So that's the goal, to assign a probability to sentences or sequence of words. They don't know any sentences, okay? Now, why do we need a language model? So you have a sequence of words, you want to compute its probability based on a history of text, right? So you don't just assign a probability based on your own hypothesis. you can do that. Like if you have a model that can capture syntax and semantics, you could assign a probability to a sentence without having access to history, right? Like maybe babies do that. They learn a little bit of data, but like some linguistic theorists tell you that we have a capacity, a special capacity for learning languages, and these are innate capabilities, right? So in those cases, based on those theories, we assign those probabilities, and not really probabilities, like grammatically judgments, based on those modules, right? But here, we just do it based on data, right? So there are other ways of assigning probabilities or grammaticality or semantic coherence to sentences and sequence of words that don't use a lot of data, but they have their own assumptions, right? But here, we use past data, just data, to assign those probabilities. And what is the goal? The goal is, for example, in machine translation, when we convert from text in a source language to a target language, right? As translating from English to French, you want your French sentence to be grammatically correct, right? Or semantically coherent. So if you apply a language model on the translated sequence, it gives you a probability. If the probability is very low, it might mean that your translation is not really good, right? Or in a speech recognition, you're converting audio signal, like an MP3 file, to text. So if the probability of your generated text is very low, it means that you might have some error. Or in summarization, you have a big document and you convert it to a shorter document, 3 or 4 sentences. If the probability of your generated sentences is low, it means that your summary is not good. That's the language model assumption. You might have, so there are shortcomings in language models as well. So, but it is a tool that can tell you how good your generated sentences are. For example, in dialogue systems, you get a user's input, like a query or a question, or just somebody says hello, and the robot or the machine generates an answer. You want to see if that's probable or not. And that's not the only measure. You can create a sentence that has a very high probability based on a language model, but is not good, right? So that's not the only measure, but it is one of the measures that are used to evaluate these language generation applications. So as you can see, all these applications are generation applications. They generate a sentence or several sentences. There are several ways to measure if they are good or bad. One of the ways is language model, right? So for example, in machine translation, you can have a really long French sentence from a movie, right? I don't know French, but you have a very beautiful sentence in French, and then you translate it to good morning, right? Not that good morning is not beautiful, but it's a very high probable sentence or sequence of words, right? It's very frequent, but it might not be the translation of that sentence. So it's not the only measure, it's one of the measures. Any comment or idea about the application of language models on the chat or using your microphone? No, good, listen. Okay, so it's clear why we need the language models, because you could translate that French sentence into just a bunch of words that are related to that French sentence, right? But your translation might not be grammatical. So moving from French to Spanish. So here we have a sentence in Spanish, which translate to the, if you translate word by word, it tells you the coffee black me please much, right? We can understand what it means if we translate it word by word, but if we have a language model, it will assign a low probability to this sentence, right? So if you compare these two sentences, this is a word by word translation, and this is the real translation, a language model of English. So a language model is a language model of a specific language, right? We have multilingual language models as well, but usually when we have a language model, it is trained on a specific language. So a language model of English tells you that this has a higher probability. So if you have a machine translation model that can generate 10 different translations, then you can use a language model of English to find out which one of them has a higher probability. As I said before, this language model assignment of goodness is not the only factor, it's just one of the factors. Now, the language model started with N-gram language models that are used even today. And maybe until 3 years ago or 4 years ago, they were the state of the art with lots of tricks as well. We will see how we can learn a language model. So usually we start with a big corpus of text, and we learn this assignment of probabilities from just counting, right? So it's about counting the word sequences. Here we have a quote from Picasso, and I'm not sure if that's true. It's really from Picasso, but I just saw it somewhere. So computers are useless. They can only give you answers, right? So this is a sentence, and language model sees that at a sequence of words, right? What is the probability of this sentence? Assume that you want to assign a probability to this. You can count the number of times this sentence has been used in a large text. For example, you take out Wikipedia text, all the Wikipedia text, and you count how many times you see this green sequence, and you divide it by the count of all sentences ever spoken, right? That is a probability, right? So this is the way one could assign probability to a sequence, but as we all now know, we don't have the count of all sentences ever spoken, right? We don't have this. And that's a big issue. So in probability estimation, we usually say that if you have 10 items and 10 items, and all of them are green, expect 2 are red. So the probability of red is 2 divided by 10, like the total count, and you have the number of reds, and you find them, right? So you find the probability. Here, if we do the same thing, you don't have the count of all sentences, so it's very difficult, right? And also, this sequence might have been seen only once or twice, or if you change this, like if you change you to us, then the count might be 0, right? But still, this is a grammatical sentence. If you say computers are useless, they can only give us answers. Picasso didn't say that, so it's not in our Wikipedia or text corpus, The count will be 0, but it is still a probability. If we change you to us, the count will be 0. Assuming we know the count of all sentences ever spoken, let's ignore that. The probability assigned will be 0. So that these are two problems for assigning probabilities to sentences using only counting. Do you see the problems? We can't count all the sentences ever spoken. And also, if you change one of these, then this count becomes 0, while it's still grammatical and semantically correct, right? Okay, so Ben is asking, could we generate all possible sentences and then count them, right? So that's possible, right? You could assume that we have 100K vocabularies, like 100K words, and assume that your max sentence length is, I don't know, 30 words. And then you can have 100K to the power of 30, right? So it's a very big number. We could have an estimate right there. Yes, so that would create the ungrammatical sentences as well, but maybe will give us an estimate, but it's not a good estimate. Yes, Hunter?
Hello. So how do you draw the lines between one semantically similar sentence and a different one? If I give you the question, computers are useless, I'm getting the wrong answer. That might be a technical question. Whereas just changing the sentence slightly completely changes what the question is. How do you draw the lines between a certain type of question to give you the certain kind of results that you're after?
Okay, so the goal is to assign a probability to two these sentences, and we change one of them slightly. If I understand your question, we change one of them slightly, and that completely changes the sentence, right?
Yeah, if you change a few words, you might change the entire meaning of the sentence, or even just one word, which might direct where you want to send a request.
Yeah, so it's like negation, right? If you use just a not, it changes the sentence.
Yes.
Right?
Yes.
So this is something that language models are not good at, right? So that's one of the shortcomings of language models that are a little bit addressed a little bit in neural language models, right? So where they use context in a different way. So here we have a context and a word that is changing. Depending on the context, changing of that word might change the whole sentence, the meaning of the sentence. So yeah, so that's an important shortcoming of these language models, and it's good to think how they work and what are their shortcomings. Good hint. And Lucinda, does it matter what the denominator given that it's always the same? Not really. It doesn't matter that much, right? So you could, because if the goal is to compare two sentences, so Lucinda is saying that for all sequences, this count will be the same, right? This count will be the same. So if you want to compare the probability of two sentences, it doesn't matter what the denominator is, right? So that's correct. If you want to compare two sentences, it doesn't matter what that is. But the second problem still exists where the count of this one might be 0. Good question, right? So this count could be ignored if you're just comparing two sentences. Okay, a little bit of background on joint, marginal, and conditional probabilities. Assume that we have 32 students. Some of them got grade A, B, or C. So we never had a D. That was good, right? So these 32 students have these grades, and each one has a favorite food, right? So some of them for like pizza, curry, noodle, soup, all this. And they only have one favorite food, right? They can't pick two. So we sent a survey, they picked their favorite food, and also we know their grades. Now we can become familiar with probability concepts. So that's just a reminder. Some of you might know. For example, here we have two people that got A and their favorite food was curry, right? Or here we have three people that got a B and their favorite food was soup. Here we have the marginal probabilities of marks, and it's just counting how many people got A. 4, 2, 1, 1, 8 out of 32, and 8 divided by 32, we call this the marginal probability of A. We can show it like this, or P of A, or P of mark equal A. So if you see these concepts, they mean the same thing. So this is the marginal probability. What is the joint probability? The joint probability is the probability of B and cherry, for example, B and cherry, which equals in writing to P of mark equals B and favorite food equals cherry, which is 6 divided by 32, right? Now, the conditional probability is when we want to know the probability of mark equals B, given that we know their favorite food was cherry. So that's how you read the conditional probabilities. What is the probability of having a mark B, given that we know their favorite food was cherry? So this, given that we know, limits our scope, right? So we are now just looking for people whose favorite food was cherry, and that equals to the joint probability of these two. So the probability of mark was B and favorite food was cherry, divided by the probability of all the people whose favorite food was cherry. In another way, you could say that what is the conditional probability of B given cherry, right? So we know that their favorite food was cherry, right? So we have 8 people who loved cherry. Now, from these 8 people, 6 had a mark of B. So the probability of getting a B, while we know their favorite food was cherry, is 6 over 8. The probability of C given cherry is 0. The probability of A given cherry is 2 divided by 8. Do you see it's not 2 divided by 32 anymore? Because we know they love cherry, so we just divide by the number of people who love cherry. So that's just a reminder. So let me see if I can actually share something. I hope it works. Okay. Okay, so here we are looping over all the favorite foods and summing the probability of having an A. So which one of these two is correct? So here we can say M equals marks. So here we're looping over all marks. And here equals L. And favorite food, F equals favorite food equals F. So here on A, we are summing mark is A given a specific favorite food, and we are looping all favorite foods that are possible and summing the probabilities. Here we are looping over all marks given that our favorite food was cherry. Which one do you think is correct on the chat? Don't be afraid to make mistakes. I have made this mistake so many times, but it's good to think about it and like get an intuition behind this, and then you learn conditional probabilities. So don't be afraid to take a mistake. Which one is correct on the chat? So we have one answer. Students? So there have been times I had said B, there have been times I had said A. Yeah. Sure, Janet. Okay, students, you don't want to make a mistake? Just make a mistake, that's okay. Okay, so if we can use non-categories in top. Yeah, so here we just have categories. Yes, so there is a probability. So Ben is saying there's a probability that one of us is correct, right? So this one is correct, right? So thank you for all who answered. So this one is correct, and this one is incorrect, right? Why is that? So this is based on the table that we had before, right? So if you know that the favorite food was cherry, then as you saw in the table, we had 8 students who love cherry, right? From these, 6 got A, 2 got B, 0 got C, right? So what we are doing in B, we are saying 6 over 8 plus 2 over 8 plus 0 over 8, right? So when you see these sigmas, and you will see this in papers, and I was usually afraid of them, when you're summing over here, you're looping over here, then the sum should become 1, right? But it's not the same when you're looping here. It doesn't have to be 1, right? So in this case, it doesn't have to be 1. Okay, so when you see these sums, it is only a loop. So if we're talking Python for mark, in marks, then find the P of M given carry, and then sum them together plus equal this. So this is what this sum means, right? Okay, so that's enough for now. Yeah, so Hunter is talking about if it is a category or if it is continuous. So yeah, so the intention here was just talking about the table that we saw here. So a little bit, we talked about probabilities. Why we did that? Because we will talk about sequence of words and their conditional probabilities later. And what does that conditional probability means? It means that the probability of face mask, given that we wrote a sentence before, right? That's the conditional probability. Okay, so these are all based on Bayes' theorem. And we usually, like not usually, always, we can convert a joint probability. And now you know what joint means. So joint means here, right? This is the joint probability. We can convert that to a conditional probability. So if you have the probability of a sequence of words, and we saw that we cannot measure that because we didn't have the denominator, we can convert that to a conditional probability. So P of W1 multiplied P of W2 given W1, P of W3 given the past history. So for each word, we have the conditional probability of this word given its past history, right? So for the last word, and assume this is a text core document of, I don't know, 1,000 words, right? So this is P of the last word, P of W1000, given all the 1999 previous words. And this is an exact equation. So this is always true. This is a mathematical exact, no approximation here. So each element in this product is the probability of a word given its predecessors or history. For example, so one way to compute that is P of useless given computers are, so a word given its history. And how we compute that, we estimate that, we count the number of times we have seen computers are useless and divide it by the count of computers are any vocabulary, right? So you might have sentences like computers are useful, computers are smart, computers are stupid, all those things. So you count all those things in the denominator and you count how many times you see computers are useless. If you divide these two, you get the probability of useless, given that we know the history is computers are. And this denominator is just equals to count of computers are. So you count this part and you divide the whole sentence divided by this part, right? So here you are seeing how we can compute this one, right? So if our sentence was computers are useless, you would have a P of computers multiplied P of computers, P of R given computers, right? P of useless given computers are. And if you did that multiplication, you could break the big sentence into a smaller ones. And that's the goal, because here you're breaking the long sentence into a smaller parts. However, you still have this long sequence here, right? So here, these are a small parts of our equation that you can compute, right? So if we have a very long sentence, these parts are small, like it's just one word, or one word given one word history, one word given two word history. These are still small. So it's highly likely that we can see that in our corpus. But if you go along this and our sentence is a long sentence, at the end, you still get a very long sentence whose count might be 0, right? So we still have the problem that we had here where counts could be 0. If you just change this u to us, the count will be 0, and then the whole probability will be 0. So that's a problem here. And how we solve it? In computer science, when you can't solve a problem, you just ignore it, right? So here, if you just ignore this part, then you get a solution, right? So you can say that I just computed until here. So that's approximation. So that's one way to deal with these long sequences, just ignore some part of it, right? So it's not as simple as I mentioned. So these are different approximations to computing that joint probability or conditional probability. If you can compute the conditional probabilities here, you can compute the joint probability, and then you can assign a probability to a sequence. Now, we saw that we have a problem here with very long sequences on the condition, right? Because this count might be 0 because it's a long sequence. What we want to do is to approximate it. So one way to do that is we have P of M given M-1, M-2 until W1. For example, if we had this sentence, assume this is this sentence, from here to here, this is like probability of ones given all these sentences, all these words, right? So this is what we have here. This approximation, which is a unigram language model, tells us that that probability could be approximated, but just the probability of ones, right? So that's one way of approximating this conditional probability is to say it's not even important that is conditioned. We just say how frequent the word ones is and divide it by the total number of words, and that's our probability. Which is not good because it doesn't consider the context, right? For example, in such a unigram language model, the probability of the word of or are or stop words or function words will be much higher than content words, right? Because they are more frequent. So if you train a language model, you will always get a high probability for these stop words, function words. Now, if we go one further complex to have a better approximation, we could say that the probability of a word given all its long history just depends on its previous word. So here, WM is ones, and this long sentence is the whole sentence here, and we approximate it by probability of ones given simpler. So we only consider the previous word, right? And that's a conditional probability. We call that a bigram language model. We can increase the context, right? Ones, P of ones given the simpler. Give of ones given one of the simpler, right? Then we have the n-gram language models. So we saw a way, we broke down the joint probability into conditionals, and then we simplified the longer ones using approximation. And approximation can be simple, like unigram language models, or more complex. So one example, P of computers are useless equals to P of computers multiplied by P of R multiplied by P of useless. This is a unigram language model, right? So for example, P of computers equals count of computers divided by count of all vocab, like the size of your whole text corpus, right? Or you can go more complex, say P of computers are useless equals to P of computers given the start of a sentence multiplied P of R given computers multiplied by P of useless given R. And when you want to compute each section, you can count the computers R. For example, if you want to compute this probability, this is a bigram language model. You have count of computers R divided by count of computers. We could go further into trigram language models, as you can see here. P of useless given computers R. So for these ones, we didn't have a longer sequence, right? So we didn't put it there. So if you look at this equation or probability, it is similar to here, right? Do you see? So these are the first three sentences. Up to here, it is a bigram language model. So usually you can go up to 5 gram with a very large corpus, for example, the whole English Wikipedia, but then you will face efficiency problems because if you want to store this, so if you have 100K vocabulary, you need to keep 100K probabilities for a unigram language model. But if you have a bigram, right, you have a much larger space required. So then you need to keep a matrix instead of a vector. So one problem with going higher and higher in terms of our approximation is that at some point we will face the same problem because we get a long sequence and the counts become 0 or very sparse. And our language model requires a lot of parameters. You need to keep the probability of every word given every possible context that you have seen, and that's a very large parameter space. So more formally, if we have a sequence of words, like a big text corpus, an n-gram language model approximates the joint probability as conditional probabilities up to a history, right? Not the whole history, but up to 2 or 3 words. And that's the n. If n is too small, so the history that we see is very small, like 1 or 2 words, it doesn't capture long distance dependencies. For example, assume that we have a sentence like gorillas always like to groom their friends. As you can see, there should be consistent with gorillas, right? It's plural, and this should be plural too. But if you have a bigram language model, when you want to have like a prediction of probability of there given to groom, you have not seen gorillas here, right? So you don't know if this should be plural or singular if your language model is small, like it's a bigram language model. So you need a 1, 2, 3, 4, 5 gram language model to see this dependency. 6 gram actually. So I didn't count this one. If n is too big, if n is too big, you will see a long sequence here. One problem is that many of the n-grams will not occur in training data, but when you want to assign a probability to a new sentence, you will see them because the language has a lot of variability, right? So you didn't see that in your training data, in your corpus, so the count is 0, but you see it in your test data and you have no idea. The probability becomes 0. Also, the size of n-grams grows very fast when n goes up. For example, if a language has 100K vocabulary, and we want to store a 6-gram language model, we'll need to store 100K to the power of 6 probabilities. Many of them will be 0, but you still need to have them, right? So these are issues and problems with n-gram language models. And there are strategies for each of these to make them better, and it makes them much better. But these are out of the scope of this lecture, right? There are several methods that are not covered here. So you can make these language models much better, right? And still in many applications, they might not be using neural models. They might be using these models because these models are explainable, right? You can easily tell someone that I predicted face mask for you because in our training data, the count was higher, or the probability was higher. Okay, so this is just an example. Assume that our corpus is these two sentences. This is a symbol of a start of sentence. This is end of sentence, like that. So we have just two sentences. From that, we have a vocabulary, which is a start of sentence, yes, no, and end of sentence. And the question is, how many probabilities do we need to store for a trigram language model? It is the size of vocabulary to the power of trigram 3 to the power of n. So if you want to train a language model for these 4 vocabularies, and it's a trigram language model, you need to keep 4 to the power of 3 parameters or probabilities, because you need to have this word conditioned on this and this word, this word, this and this word, all the combinations. If you count all the combinations, then you will see that it's count the size of vocabulary to the power of 3. Now, given this corpus, this vocabulary, and that we need to learn a trigram language model on this, what is the probability of this long sequence, right? So it is a trigram language model. So P of this long equals to P of no given a start of sentence, P of yes given a start of sentence no, it's history, then P of the second yes given no yes, then P of no given yes, yes, then P of end of sentence given yes, no. You see, for each token, as they call it, or word, we are getting the conditional probability of it given past 2 words, because it's a trigram language model. So for try, we count a history of size 2. Now, to compute this, each one of these parts, we have the conditional probability rules, right? So P of no given a start of sentences is count of S no divided by count of S. So have a look at this and think about it and ask any questions you might have. So after this, you should be able to, if they give you a very large corpus with a vocabulary that you can extract from the corpus yourself, train a simple trigram language model and be able to assign a probability to a sentence. So have a look at this and see if you have any questions. Any questions on the chat? Is there some of these probabilities that are not well explained or confusing? No? So we have, makes sense. So within the, says makes sense, that's good. So you might ask why here in this place. Yes, Ben. So sometimes it's uppercase and lowercase. That's just my bad formatting, and also PowerPoint fixing all the P's at the beginning of sentences to uppercase. There was no intention in that. So yeah. So you could all write it in lowercase or uppercase. Thanks, Ben. Yeah, so these P's are the same. And in the beginning, you don't have a bigram here, like it's a trigram, so you should have two history, but we don't have it, right? Yeah, so no pattern then. These P's, it's just my mistake. I should have fixed it. Okay, so now assume that we learned all these probabilities, probability of every word given 2 words before from this corpus and this vocabulary, then we have a trigram language model, right? And then given a new sentence, this is a new sentence, we can assign a probability to it using these conditionals. So how do we evaluate a language model? Now you're able to train a language model, find the probabilities, keep it somewhere, and apply it on a given piece of text. How do we know our language model is good? One way is extrinsic. You apply the language model in machine translation. You have a machine translation model, and it generates 2 different translations. You can assign probabilities to that and see which one is better, and then compare it to human judgment, right? So that tells you that if the preference of your language model is the same as a human native, not native speaker, but someone who knows the language, then your language model is good. But if it doesn't agree, in many cases, it's not good, right? So that's extrinsic evaluation using an application that uses language models. Another way is that you have trained your language model on a corpus, right? Now you pick a new corpus that is different from the previous one. So the previous one was training. You pick a new unseen corpus, the corpus that you haven't seen during your training, and you assign a probability to that corpus or the sentence of that corpus. Then you get a probability for that test corpus. If the probability is high, it means that your language model is good. Why? Because that test corpus was real language. The probability should be high, right? Sometimes, so we want a high probability. Sometimes they use an inverse of probability, call it perplexity, and we want that to be low. So instead of finding the probability, we have the inverse of it and mth root, and we call that perplexity. We want that to be low. So you could say that probability should be high or perplexity should be low. So they are the same thing. So 2 ways of evaluating language models. Now you know how to train language models. Also, you know how to evaluate them. So that's good, right? Now going back to our first question, how do search engines predict what we search for? Yes, so Lucinda says that perplexity is, is an interesting name. Yeah, so it's fancier than probability, right? It seems philosophical. And maybe it is, I don't know. Okay, so going back to our first question, how do language models predict the next words? So how do they do that? We want to have the probability of how to make face masks more than probability of how to make pancakes, more than the probability of how to make a mask, right? So you can see here, the probability of this sequence is higher than this sequence, and this is higher than this sequence because of the specific corpus that this language model was trained on. So if you change the corpus, these probabilities change. If you change the training corpus, these probabilities change. So usually search engines have a general one that is always there, and also a temporal one based on temporal events, and they combine them somehow. So they are trained on recent submitted queries, and you can see that here. So this was from last year, where face masks were very popular. Not today. Okay, so up to now, we saw that we can assign a probability to a sequence of words. But language models can also talk, not the real talk, but language model talk, that they can be used to generate text. If you train a language model on one or more words, so if you have a language model and you have a history, you can, from the history, you can predict the next word, right? How can you do that? For example, assume that you have a trigram language model. When they say you have a trigram language model, it means that you have those probabilities, those conditional probabilities. You have the probability of every word given its past two words, right? So when they say you have a language model, it means that you have those probabilities with all combinations that happened in your training data. So you have those probabilities. You want to predict the next word after I am, which is our history. So you go and find those two words in your probabilities. What is the word that has the highest probability? You already have that in your probabilities, right? So you pick that one. So you might say, I am what? A very probable word. I am a something, right? So the next word might be a. I am a, I don't know, language lover, right? I am a language lover. So usually after I am, we might have a. So I am a. And if you look at your parameters that you have learned from your training data, a might be the most probable word. And then when you predict a, then you have I am a. You look at am a, what is the most probable word after? So here, assume that W3, you predicted it to be a. Here you have am a. What is the most probable word given am a history? And this is based on your training data. And you can just generate one by one based on your trigram language model. Do you see how we can generate text from a language model? Is anything unclear here on chat? No? So everything is clear. Good. Exactly. So Lucinda says, just like predictive text in SMS, yeah, it's what it does. So in your text, when it predicts something, it's exactly that. It's the language model. And even for your spell checkers, they use the language model versus a similarity checking to see if you have any errors. And depending on the corpus, it might change things, right? If it is trained on your own data, it will be more precise, but also more sparse because you don't have a lot of sentences. One issue with language models is that they don't consider word similarities, right? For example, assume that in your training corpus, you have a sentence like the movie was fantastic. You have somebody has seen a movie and they say the movie was fantastic. So the probability of fantastic given movie was, this is a trigram language model, right? Because you have 3 items here. It's a trigram language model. You have stored all the probabilities. So the probability of fantastic given movie is not 0 because you have seen this sentence in your training data. Now you go to test it on your SMS, right? You're trying to do an SMS and you say, movie was awesome. But the language model on your device has not seen awesome before. So it thinks that its probability is 0, right? Because if you look at the parameters of your trigram language model, it has never seen, assume that it has never seen awesome given movie was. So if it hasn't seen that, the probability is 0. So it says this is ungrammatical, right? And it doesn't consider that these 2 words are very similar. So that's a big issue with just basic n-gram language models. Right? Is it clear what is the issue with n-gram language models? They don't consider word similarity. And that's a big thing because in language, you have so much freedom to use different words in different contexts that not a single language model can learn all those things. And n-gram language models are not designed to capture that. As I mentioned, there are tricks that people apply and they work much better, but pure n-gram language models, they don't consider word similarity. So the probability of movie was awesome, or the conditional probability of awesome given movie will be 0. So a summary of language models. They capture the predictability of language. They require to store large amounts of probabilities. And as you go from trigram to 4-gram to 5-gram to 6-gram, your data becomes sparse because you could have so many 5-word sequences and many of them might not happen in your training data, even though they're grammatical and correct, and somebody might say that, right? Language models can be used to generate text. So you saw that we can get the history, look at the parameters, see which one has the highest probability and generate that, right? Then look the next 2, predict the next, and just talk like that. And they ignore word similarities. Now here comes the neural language models that have transformed the language technologies field. And the main idea is that they consider word similarities and they do a fantastic job. Not that they are perfect, they're not, and they have so many shortcomings, but the language that they produce is scary and very interesting. If you haven't seen them before, it's so interesting to work with them. So neural language models, the goal is still to be able to assign these conditional probabilities, but they don't do counting, right? They do prediction. What they do is that they get the history. So this is, assume this is a neural network. Doesn't matter what it is, the black box. It gets the history and tries to predict next word. So I am A goes here into input, and we want to predict the next word. And we know what the next word is in our training data. So we try to predict the next word that we have seen. For example, if we have I am a student a lot in our training data, every time that we see I am a student, I am A goes as input, and the neural network tries to predict the student. So it predicts a probability for all the possible words, but it makes sure that the probability of a student is higher, right? And if the assigned probability to a student is not high, it changes the parameters of this model so that next time it is higher. So every time it sees I am a student, it changes these parameters so that the probability of a student, predicting a student, goes higher. And it does this for all the sequences in our data, in our corpus. So at the end, it somehow learns both word similarities, and also it can have a longer history because the number of parameters required to store those information, those counting information, is much lower. Here we don't count, but in a way the language model is learning to do the counting with a lot lower number of parameters in a way that is not explainable, right? So it's a mishmash of neurons, not the bioneurons, the computational neurons. And the combination results in being able to do this counting. And nobody knows how, but they do that. So there are several types of neural networks that are used, and it is these transformers that have transformed the field of natural language processing. So these transformers are really good at capturing long context dependencies between different words. Do you remember that gorillas and deer? So these ones, they are really good at that. They can easily find the long distance dependencies. And also they consider the word similarities because they use a concept called word embeddings, where you have a vector for each word, and the vector of awesome and fantastic are close to each other. So that's a more complex feature. The words, the ground there goes in. Here you get the word embeddings. And then at the end, you make a prediction for all your words. So here you are making a predictions for all the words in your vocabulary. One of them that is the highest will be used when you're predicting, right? When you're generating a language. Okay, so this is a really good book if you want to know more about language technologies, and I think it's freely available online. That's at least some preprints. Okay, so what makes the difference in neural language model? They use word representations that are called word embeddings, and you can click on this link. Let me see if I can actually do that. Okay, so when you have access to to the, so this is word embeddings. So these are like 100-dimensional vectors, and here they are showing it in a lower dimensional space where, how can I say, for example, temperature, televisions, tanker, I don't know how they are related. So here it's supposed to have words that are similar to be close to each other. For example, what about these two, cart and asteroid and boot apple? I don't know what the relation is between them. Pipe contains, there's some kind of similarity, and it's not very explainable, but you expect things to have a similar semantic meaning to be close to each other, but I don't see it here. So you can play with it. Why is it not really good? What do I get? So this is very heavy. No, don't choose that one. It takes a long time. I did a mistake. So one reason for the fact that these are not really good is that it's moving them into a smaller space. So you see these are really related. So proteins, enzymes, what is it? Metabolic, do you see? So things that are close semantically and also sometimes syntactically, they are close to each other. So this is not the real vectors. The vectors are 100 dimensionals, for example, but these are reduced to 3 dimensions using a technique called PCA that you don't need to know. You can just go and play with them. So going back to what we were talking about, one difference of language models, neural language models, is that they use word embeddings. And the other one is that they can capture long distance dependencies. Why? Similar to large n-grams, because they don't store so many parameters. They don't need to store all the possible probabilities. They are more efficient in terms of the number of parameters. So they can capture longer distance dependencies. Also, neural language models, similar to n-gram language models, they can be trained in character level instead of word level. So you had a history of words, sequence of words before. You could have a sequence of characters and predict the next character. So in some applications, this might be more interesting, and go and see that. So there's a link there that you can go and you can see the text. So they train it on Shakespeare's books, and they start generating these characters. And it's very nice, right? So these are generated by a character-based neural language model. And this is so good. It's just a 3-layer RNN. Not that they are good poetically, but like if I saw that, I wouldn't say this is generated maybe by a bot with first glance. So it is learning the words, right? Remember that it is being trained on characters, not words, but it is learning that it should put a space between different words. Okay. Let me share the screen again, and we had a comment on chat. So, Oh yeah, so you learned about PCA, that's good. Hunter, can you, so the question is on the chat, can you find P of a speaker equals Hunter given a random Zoom comment with a novel combination of words from the chat? I know this will not work for regular language models, P equals 0, null combination, but can neural language models overcome this? So what you're saying, you want to predict the author from their text, right? So that's the task that's called authorship attribution. You want to be able to predict the author of a piece of text from its text. Language models can be used in that way because language models are not just for generation. The neural language models, they can give you a representation of text as well. So they give you a vector of numbers. We call them sometimes embeddings or representations or encodings. And then from that, you can train maybe a supervised model to predict the author. So language models are not just for generation, they are for representation learning as well. They give you a vector from a piece of text, which you can apply a classifier on top to predict the author. Does that answer the question? Yes. So if you wanted to work with Ngram language model, you could put the name of the author at the beginning of every sentence that that author talked about, but then you wouldn't be able to deal with long distance ones. Yeah, so it will be more complex to do that. Now, so you have links to, so these are the new language model, BERT, GPT-2, and GPT-3, right? There is a difference between them. When in BERT, we talked about that language models just make predictions, right? So the GPT-2 and GPT-3, they make just predictions for the last word, right? For the next word. While BERT, given a set of, a sequence of words, it might want to predict a word at position 2 or position 4, right? So it makes predictions on different positions. GPTs, GPT-2 or 3, these are called autoregressive ones. They just make predictions for the next. These are specialized for generation. The GPT-1, 2, 3, they are specialized for generation and they just make predictions during training for the next word, while BERT is not autoregressive. They are more used for representation learning to get a vector from a piece of text for different applications. These are trained on very large amounts of text that has so many different contents. Some of them might not be very pleasant, right? So, and so they learn a language model from those texts. And when they're generating text, they might generate bad things as well. So you cannot just not talk to your children or like your, and just let a GPT talk to them, right? So they might learn very bad things. Okay, so how can we use these language models? What are they useful for? They are useful for many tasks. For example, it might give you some initial ideas for writing something. So you write the context, it just throws some writing. It might be garbage, but you might get the idea what it's doing, not because it's thinking, but because it's using all the previous people who have written something in this context and it's throwing them out and you can see them and get an idea, right? And because the text is grammatically correct, you might actually start using those template sentences and change them a little bit to write something. But they can also be used to create a spam, misinformation, toxic comments. They can generate sentences, short sentences that nobody understands. They are not from a human, right? So the sentences they create, they're very similar to what we write. And if somebody is just training a language model to answer to people who are, I don't know. So like it can just, people who oppose an idea, like a dictatorship, can just train a model to write comments to people who are opposing their idea. And then you think so many people support that dictator, right? So that's possible. And you can detect if they are a bot, they are a language model, or they are real people. So you might think, wow, so many people are supporting that dictator, so they should be good or somehow good, right? So it can be used to harass people, to create a spam. Also, they can be used to improve applications such as translation, summarization, dialogue, etc. So they are very useful, but they have shortcomings as well. They can be used for bad purposes. So there's a link to a notebook here where you can train a count-based Ngram language model and generate sentences with them. And also there is some code here and a Docker image where you can generate sentences using GPT-2. So this is I don't need to teach these things. This is Python code. You can run it and get some results. I don't know. Yes, so on Friday, we will do this count-based model, and you can just copy paste this code and run it. And I'm sure there are better codes so to generate words. Yes, so on Friday, you will do both. That's good. So I don't talk about this coding thing anymore, but let me share with you. Okay. So this article is written by GPT-3, which is an autoregressive language model. What does it mean, autoregressive? It means that the input is only the history. You just predict the next word. It's not like BERT that you predict the middle word as well. And then it is mostly written by GPT-3. Given a context, so they gave GPT-3 a context like, convince us robots come in peace, right? So that's the context. You need a history for a language model. They gave GPT-3 a context, and then GPT-3 generated next word, and then from that next word, next word, next word, that's what you have learned, right? And then that's this article. I'm not a human, I'm a robot, a thinking robot. I use only 0.12% of my cognitive capacity. Do you see how coherent, and would you be able to detect it's not a human if you had read this somewhere? It's very interesting, isn't it? And you can do that at home. That's the main thing. So today, you can go and generate your own articles and write a robot. Yeah, so you can it can help you to write better, especially it might be used in future in second language learning. And also it's useful for writers and for spammers and for sending misinformation. So you have conditional language models as well, where they just don't generate based on the given history. You might give them other things, like write negative things, write positive things, write motivational. Like you can say that the style of the generate context or the sentiment, you can control that as well, right? So it can be used for a purpose, and the purpose could be good or bad. So there are benefits and consequences. Any questions about how good or bad these language models are?
Ash, I heard that GPT-3 was not released because of the authors were worried that it would be used for nefarious purposes. Is that true?
Yes, so they didn't publish GPT-3 because they said it can be used for those purposes. But that doesn't mean that people cannot train them. By people, I mean like big companies or governments. So that was because there was no invention in GPT-3. GPT-3 is only a language model where the code is already there. You just need to train it on large amounts of text. If someone has large amounts of text, you can train it. There is a GPT-J that is trained. So if you go to GPT-J, this is the open source version of GPT-3 that is released, right? I don't know the computational requirements of running it, because GPT-3 required about 300 gigabytes of RAM, I think. GPU RAM, I mean, not...
yeah, okay.
Yeah, so you couldn't run GPT-3 even if you had the code. Only very big companies and governments could. But GPT-J, I think, is released and people can use it if they have the required hardware. So the code to generate GPT-J is the exact same thing as GPT-2. I don't know if I never tried it. Yeah, so it might be possible to run it on Google Cloud. I'm not sure.
Okay.
The change is just changing this name. Then we can try it. Yeah. So if you learn how to do GPT-2, GPT-J is much better. Much better. Much better, right? So if you can run it, I expect you to be amazed on how it generates language.
It's okay. We might try that on Friday too.
Sure. What else did we have here? Okay, so it's just that we learned how to train a count-based language model. We learned why we need language models, and we learned how to evaluate them using extrinsic and intrinsic perplexity or probability. We learned the shortcomings of N-gram language model and how neural language models address them using word similarity and larger context and more efficiency. And we saw examples of these big language models trained on large amounts of text and their pros and cons. Anyone have any questions or ideas about how we can use these big language models for a good purpose, or how not to use them for a bad purpose? Yes, so Lucinda says that it's worrying because these language models depend on large amounts of text that only big companies have, and we don't have that. So yes, so they can use it for their commercial purposes. Yes, so data is power, and it makes them more powerful. Yeah, so it can be worrying. And I think, in my view, those companies are not the most worrying ones. So, because they're thinking about just money, and usually to get money, you have to be reasonable a little bit. But the more worrisome is access to these technologies by non-democratic governments, in my opinion. They can change opinions easily by propagating misinformation. So in my view, the commercial use cases are not that worrying compared to how non-democratic governments can use them. Any other ideas to use these language models and start a company and earn money, or not to use them for a bad purpose? Is there much work on detecting real people vs language models? So there are works, and they show that if the sentence is short, you cannot do that, right? These language models are very coherent. If the sentence is short, 1 or 2 sentences, like a tweet, you can't detect these are human or robots. When you work on Ngram language models, you can see that even Ngram language models, without any tricks, they create sentences that seem very reasonable.
Ash, in the discussion about language models, it seems that these are all trained on, or we're working with languages where words are sequences of characters that have spaces on either side of them. What approaches are used for languages that are maybe polysynthetic, where words are composed of lots of morphemes that don't show up statistically frequently?
Yeah. So actually, I don't know.
Do people break them down into the individual morphemes and then try to do similar, use similar approaches, or is it all just in the too hard basket for these languages yet?
Yeah, so that could be one solution, but in reality, I don't know what they use for those. Yeah, I've never thought of that. So yeah, but that's one solution, right? To use individual characters or morphemes. So in English and like other high resource languages, I don't think there is a lot of work in changing how you break the sequences. So they do that based on a statistical model. These, like GPT-2 and BERT, these models are not based on words. These are based on specific subwords that are more probable.
Oh, okay. So that's,
there is no linguistic knowledge in there. They just break the words so that they call it piece words, where you have you break the words so that the sections are more probable. So it's just a statistical model, no linguistic knowledge there.
Okay, it'd be interesting to see how these approaches work on the other languages then.
Yeah, right. Any questions on the chat?